Everybody, Dr. White back again, continuing our discussion of exponential and gamma random variables. So we have derived a PDF for gamma alpha theta random variables, and that's the formula. All right, and that alpha could be any real number, not just a whole number, but when it's a positive whole number, then the random variable can be interpreted as the waiting time until alpha events in a Poisson process where you can expect to wait a theta units of time between successive events. So let's go on to some new stuff. First of all, if alpha is a positive integer, so that you can interpret x as that kind of a waiting thing, I would like you to observe that x can be written as a sum of some other random variables. x1, x2, all the way up to x alpha, where for each of the i's, xi is the time between the I minus first and the ith event. Now, those xi's are independent of each other because what goes on in different time intervals is independent of each other. So, if I have to, wait 10 seconds for my first event, then that says nothing about how long I'll have to wait between the first and the second event, So they're independent. Furthermore, each of them is awaiting for one other event. And therefore, each of them is an exponential random variable, the waiting time till the first event. So they're all exponential and they all have the same theta parameter because they're all part of that same Poisson process. So a gamma is the sum of alpha independent exponential thetas. Sorry, it keeps on bluing the screen out like that. We've seen this pattern before. We have seen it with negative binomials being the sum of R independent geometrics. So surely something is afoot. Surely the pattern will repeat itself. So like for negative binomials, the moment generating function for a negative binomial was the moment generating function for a geometric raised to the rth power, where r is the number of successes you're waiting for. With binomials, binomials were the sum of n independent Bernoullis, and the MGF for a binomial was the MGF for a Bernoulli to the n. So you would expect that the moment generating function for a gamma should be the moment generating function for an exponential raised to the number of events you're waiting for. And in fact, it does turn out that way. You can look at the textbook for the math. It's not that hard. Similarly, in the textbook, they derive the expected value and the variance, and they turn out to be as you would expect according to the previous patterns. So if you're waiting for the alpha event and they occur on average theta apart, you can expect to wait alpha theta units of time. And the variance is also alpha times the variance of just a single exponential. So that really does happen. And the way you can see it is to find the moment generating function and then use the moment generating function technique to get the mean and the variance. It's actually an exercise, number 7 in the book, to derive the moment generating function for a gamma. So I suggest that you give that a try on your own. Do see the hint that they give in that exercise about dealing with the calculus involved. If you need to, you can compute with R to get probabilities for exponential and gamma random variables. They come in the same family of functions. There's a D version for the PDF if you ever need it. There's a P version for your CDFs, and there's an R version for your random generation of such variables for simulations and things. So we'll get into that maybe in another screencast. Why don't we do a little computational example, the best we can by hand. So let's go back to the text messaging scenario where texts arrive on your smartphone according to a Poisson process. And let's say that they arrive at a rate of lambda equals 5 per hour on average. What's the probability that you have to wait more than 3 hours for your 12th message? So here's an approach that gives a totally correct answer, but I consider it to be kind of uncool. Let's see the approach. So you set up your random variable in a straightforward way. Let x be the time you wait till the 12th message. And so you say, hey, x has got to have the gamma distribution where alpha is 12. And the theta parameter is 1 over the rate, so 1/5 of an hour between messages on average. And so you just, integrate the PDF over the range from 3 to infinity, because areas under the PDF give you chances. And so integral from 3 to infinity, and you just trot out the formula, for the PDF, and there you go. So I consider that to be something of a cop-out. It involves this improper integral, which could be computed if you did integration by parts like a ton of times. But that would be awful. And it's a cop-out to just leave it like that. It would also be a cop-out to say, hey, that's 1 minus the integral from 0 to 3. That costs a cop-out too. You still got the same tough antiderivative that you would have to use integration by parts on a lot of times to get. So the cool approach really is to think back to the way we were deriving distributions for exponentials and gammas in the first place, where we switched up the random variable of interest in our minds. So my suggestion would be to stop focusing on how long you got to wait, but focus on how many events occur in a certain time. You're wondering what's the chance you got to wait more than 3 hours, huh? So why don't you focus on the number of texts that come in the first 3 hours? Call that capital X. Let that be your random variable of interest. Now that's a counting Poisson random variable. Its distribution is Poisson with a rate of 3 times 5 equals 15, because it's 3 units a time, 3 hours, 5 per hour. And the chance you gotta, wait more than 3 hours would be the same as the chance that you get less than your 12 desired texts in those 3 hours. So really, you're just finding the chance that x is less than 12. And so that's a little finite sum of the PMF for a Poisson. You just sum x is 0 to 11, rate to the x, e to the minus rate over x factorial. And so, it's still a pain, but it's like the simplest thing we've found so far. I can't really carry it any simpler to get a nicer closed form, so I'm just going to leave that. So strive for that when you're doing homework or just thinking about things. Strive for the nicest possible formulation of your answer. Sorry. It's time to step back a little bit and to think about some of the distributions we've learned about so far and the conceptual relationships between them. So we've made that distinction between counting random variables and weighting random variables. We just have some more families of random variables to add to that list. So under counting random variables, we already know about a Bernoulli random variable where you only got one trial and you're counting the number of successes in that one trial. That's a special case of a binomial where there's n trials and you're counting the number of successes in the n trials. The special case is just set n to 1. And along with that is a weighting concept. If you've got a Bernoulli process, you could be waiting for the first success, and that's associated with a geometric random variable. which in turn is a special case of waiting for your rth success in binomial. But now we can kind of add some more to the list here. So we've got a counting random variable, Poisson, that counts how many events occur in one unit of time where the rate of the process is lambda events per unit time on average. Now, there's not like a separate kind of random variable this is a special case of, but I could just say that this is a special case of waiting in units of time and counting up the number of events. That's also a Poisson, the rates in lambda. Okay, so just to have special cases like we had before, I am throwing that in. Now, over on the waiting side of things, in a Poisson process, when you wait for the first event, you got an exponential random variable, which in turn is a special case of waiting for alpha events to occur, gamma random variable. So we've added some to this nice structure of counting versus waiting random variables. Okay, by the way, there's another special case of gamma. Instead of just letting alpha be equal to 1, you could actually let alpha and theta be very specific things. Let theta be 2, so that you're expecting to wait 2 units of time between events in your process. And say that R here is just any number, and you set the alpha to be R over 2, okay? Then you get what's called the family of chi-squared random variables. So they mentioned these in the textbook, and they do a tiny bit with them. We'll do a little bit more with them later on. So you do want to keep them in mind. So their PDFs are just a fill-in of the PDF for a gamma. And their support is still all the x's bigger than 0. And they tend to have most of them have like a little one hump right skewed type of shape for their PDF. So just keep chi-square in mind, and we'll eventually do more homework and practice with them. By the way, the R there is called the degrees of freedom of the random variable, and we'll see why they use that term later on as well, once we acquire more insight into where they come from. So that's it for now. In a separate screencast, we'll just practice a little bit doing computations in R. See you later.